Good day, Math 30-1s. Last day we were specifically looking at the radical function square root of x, and we were applying transformations to this function. So there were flipping, stretching, and shifting in all 6 possible ways. Today we move on and talk about the square root of a function. So instead of square rooting x, today we're going to see this notation where we're going to see the square root of y. Essentially, we're looking at a function and then saying what would happen if we applied a square root to every y value. That's important. We're applying a square root to every y value. So the point is, again, to sketch the graph of the square root of a function and then talk a little bit about domain and range as a comparison between the two. So we'll first do a little investigate to just make sure this does make sense. We'll start off with something a little bit clean like a line. So given a function which is linear, a 1/2 x plus 1, determine the relationship between f of x, which is the line, and g of x, which is the square root of the line. So again, square root of the entire function. Let's start by simply drawing this line, and we don't necessarily need x values. We could simply plug in values, or we could use the fact that we know a line has a shape of mx plus b, a y-intercept is a 1, and the slope is a 1/2. So rise 1, run across 2. Rise 1, run across 2. And we could keep this pattern going and draw as smooth a curve as we can. So this makes a very linear shape, and here is f of x. Now, we could have also chosen some x values and plugged in very specific y's, but the danger in this is that we're about to do some square rooting, and not always are the outputs convenient. If I had chosen the perfect x values, things do line up very, very nicely, but I'll save that for a moment. Now what we are going to be doing is determining a new function, g of x, which is determined from the square root of this function. So what we're going to do is follow along with our pen or pencil and ask about y values. So we're focusing only on y values. I'm going to start up here, and I'll say some y values as we go, and we're going to square root some in a moment. So here's a 5, 6, 7, 8. Actually, right up here would be a 9. It's a bit off the grid, but that's okay. This is where a 9 is. So I'm actually going to take this 9, y value of 9, and square root it, which travels straight down, and say the square root of 9 is a 3. If I were to keep going and say 8, 7, 6, 5, 4, 3, I could square root all those y values as we go, but the square root of 7 and the square root of 6 and the square root of 8 and the square root of 5, they're all kind of inconvenient. So I'm actually going to stop when I got to the square root of 4 and actually do a calculation here, because the square root of 4 is 2. You can see how the function, when we square root it, is kind of coming down. Square root of 3 is inconvenient. The square root of 2 is kind of inconvenient, but we could estimate those. The square root of 1 is 1. This is actually invariant. And the square root of 0 is 0. The square root of -1 doesn't quite exist, and nor does anything beyond this into the negative side of y. So we have this shape that appears to kind of curve. There's actually one interesting thing that happens right around here. When you square root a y value like a 1/2 or a 1/4 or 3/4, the value actually gets larger. If you wanted to try, square root 1/4. So right here, the square root of 1/4 is actually 1/2. And what happens is there's this inversion that kind of happens. That's a very small piece of this conversation, but that does happen. So this is actually your new function, g of x, which is the equation, the square root of f of x. And just for fun this time, I'll rewrite in the entire equation. Now instead of talking about this as a transformation with a b value of 1/2 horizontally stretching times 2, and maybe factoring that out, we could figure out what the shift is and talk about shifting this 2 units to the left. we'll stick with a different way of thinking right now and talk about vertically square rooting y values. Now, if we had chosen to pick x values and plug them in, we would end up with some values like 0, 1, 4, and 9. I chose very specific x values to like negative 2, which says 0, 0, which spits out a 1, 6, which spits out a 4, and technically 16, which would have given us a 9. So you could get very, very intuitive and careful and try to pick the perfect x values, which create very nice numbers to square root, but I don't think most people would have that much foresight to do that. So simply by seeing the original function, square rooting the y values, this isn't so bad. A few interesting questions come out regarding domain and range. For the original function f of x, where does it exist? What is the domain? I see for the original function it going forever to the right, forever to the left, so I might say the x values are such that x is an element of the reals and it exists forever left and right. In interval notation we would see from negative infinity to positive infinity. The square root of f of x, though, does actually continue to the right, but there is a bit of an issue. It stops existing at negative 2. So we could say this exists for all the x values such that x is greater than or equal to negative 2. Or we could use interval notation and say from negative 2 on to infinity. But there is a shift in what we're seeing for the domain and the range of a square rooted function. So as we start to examine maybe more complicated functions, there's going to be some issues with domain and range and what we see. Now, the domain is based on a restriction of f of x. The range is based on what comes out of that. So typically the lowest value that we've seen in many cases is a 0 coming out of the square root of x, but unless that shifts up and down or flips, things could change. So what we're going to do is determine the domain and range for each function and draw a quick sketch with our calculator just to see what that looks like. So for this one, we have the square root of x, which is our traditional half parabola. And what's the domain? Well, the inside has to be 0 or more, so we could say, well, the domain is everything from 0 on to infinity. What's the range? Well, this seems to exist from x-axis up, so also from 0 on to infinity. How about for letter B? Well, again, instead of thinking about shifting and where this ended up, let's simply say, when is the inside greater than or equal to 0? We could then solve for x and say, when is 3x greater than or equal to 1? And when is x greater than or equal to 1/3? This gives us our domain of x being greater than or equal to 1/3. In our range, let's just check to see what's maybe happened as a visual. Thinking a little bit about transformations, we know that there is no shift vertically upward, but it seems like there is a little bit of a maybe horizontal stretch and shift, shift 1/3 to the right if this was factored. So we should see that there's a 1/3 for an endpoint, and because there's no vertical shift, we're kind of confident enough to say that this is still just a 0 on to infinity. In this one, I do see a vertical flip, so nothing affects our domain. Still, the inside has to be greater than or equal to a 0. For the range, again, if in a vertical flip, we're seeing the graph flip underneath, and there's your vertical flip. So we might say for the range that this exists from negative infinity on to 0. Remember, it's always the smaller value that should come first. And for the last case, letter D, what has occurred here? Well, this is actually the very, very same thing as letter B with one change. There's a vertical shift. So the domain should still be unchanged, as the inside has to be 3x minus 1 is greater than or equal to 0. So for the domain, I'm going to stick with the same thing from 1/3 on to infinity. This time for the range, this vertical shift 3 up does impact this so that it goes from 3 on to infinity. So this will shift 3 to the 1/3 to the right and 3 up. And there is a rough sketch of where this would exist. Now, so far I've only given us linear rooted values. For the very bottom, what's a little bit different is now I'm giving us the square root of a quadratic, the square root of a quadratic. And they're typically a little bit more challenging. What many people would struggle with is trying to say, when is the inside greater than or equal to 0? This is a concept that is taught in 20-1, but many people do forget how to attempt it. If you were trying your best but forgot, you might start solving for x and say, when is x squared greater than or equal to 9? Square root both sides to say x squared is greater than or equal to positive or negative 3. And then what does that mean? There's negative 3. There's 3. X is greater than both of those. Is that what that means? Well, this logic is going to shift a little bit because when we're square rooting with inequalities, it's not quite as simple. What we are going to do is think about quadratics and restrictions graphically, visually. So I'm going to sketch the underside, x squared minus 9. That's a quadratic that is shifted down 9. Thinking about x-intercepts, this crosses about a 3 and a negative 3. Again, this is shifted down to a negative 9. Big question is, we're going to be square rooting all of these y values that come out of here. So, are there any values in here that can't be square rooted? Everything under here is negative. So imagine plugging in an x value of 0. Negative 9 comes out. So plug in a 0, you get a negative 9, and the square root of negative 9 doesn't exist, so you could not use x equals 0. In fact, any of the x values between negative 3 and 3 would not work. So where does this exist? If you pick any x value 3 or higher, you will get an answer that comes out of here. If you pick any x value at negative 3 or less, you will get an answer that comes out of here. So we can say that our domain is x is such that x has to be less than or equal to negative 3, or x has to be greater than or equal to a 3. We can't quite make one statement to combine these together because it is not possible to give me one x value that is both greater than 3 and less than 3, negative 3. So we do have to write this as a separate statement with an or. So this is one example to approach visually. Another example is a bit unique where it has an x squared shifted up 4. What would happen if we square rooted all these y values kind of like we did on the previous page? Whatever number this is, it'll get square rooted, square rooted, square rooted. All the values will kind of come down, and it should look something like this if you square root all the y values. I guess maybe a bigger question is, could you tell me an x value that when plugged in would make this not exist? You could try negative values, you could try 0, but in fact any x value you plug in will work. So as a domain, you could actually say that this exists everywhere. And we can sort of see that as the square root of the green graph. As a range, where does this exist? Well, the lowest this graph ever gets to, thinking graphically, the lowest this ever gets to is the square root of 4, which is a 2. So the lowest the orange graph ever gets to is 2. So I feel confident enough to say this exists from 2 on to infinity. Again, when we're dealing with these graphs, you can have this one as a bit of a try if you like, but what you would be doing is sketching a slope of 1, a y-intercept of 5, and you would at some point be taking the square root of all the y values. But because we did one that was similar a moment ago, I'm going to go on to something a little bit more challenging, a quadratic. Now, what would happen if we square rooted all of these y values? The good news is we approach this the exact same way. Here are a whole bunch of y values. We'll ignore the x's for a second, and we'll square root them. We'll be strategic about where we stop them. Square root of 11, not very nice. Square root of 10, not very nice. Square root of 9, sure, that's a 3. We'll travel straight down, there's a 3. Square root of 8, square root of 7, square root of 6, square root of 5, square root of 4. Square root of 4 is a 2, straight down. Square root of 1 is a 1, square root of a 0 is a 0, and again we start to make this shape. Now again, the square root of these negative y values don't exist, so we actually stop right here. It's going to be very symmetrical on the left side as we sketch the square root of 9 is a 3, the square root of 4 is a 2, square root of 1 is 1, square root of 0 is a 0, and we get this shape that again appears symmetrically on the other side. Now this is in fact the square root of the function above. Without telling you what the equation for the function above is, you could see that this is a quadratic shifted down 1, and it has the shape of 1 over 1 up, so there is no stretch on this, and it is in fact x squared minus 1. But we wouldn't need that in order to answer this. Now, it is a good activity to sketch in your calculator just to see what it does say, to make sure you get a very, very similar visual, because not always are you going to have a piece of grid paper that you'll do this with if you're on a diploma or a larger test. So sketching in your calculator is good to do. Determine the domain, the range, and the invariant points. We'll start with the domain. Where does this exist? Here's a x-intercept of 1, x-intercept of negative 1, and it exists on the right and the left of those two values. So you could say the x values are such that x has to be less than or equal to negative 1, or x has to be greater than or equal to a 1. As a range, this exists at a cutoff of 0, because the square root of 0 is 0, that's the lowest it gets to, so we could say that the y values are such that y is greater than or equal to a 0. The last part of this is asking about invariant points. And I did comment on the 4 invariant points that did not move. Invariant means they do not vary, they do not move. These points did not move because the square root of 0 is 0, the square root of 1 is 1, and so those points do not in fact move. Now if you do this in your calculator as an intersection at these locations, you might get very nice answers, you might get decimals. It's very, very convenient to get your decimal answers, but we'll do this as an exact answer just in case we are asked for exact answers. So let's start with the y value of 0 and try to get these two locations, the y value of 0. We can plug 0 into either of the new equation with a square root around it, or the original parabola, because they both are meeting at the same place. So I'm just going to start with x squared minus 1 and say the y value is a 0. By solving for x, we get a positive or negative 1, which kind of makes sense. So we know that when x is 1, y is 0. When x is negative 1, y is 0. These are 2 of the 4 invariant points. The other set comes from the y value of 1. So similarly, if we say that the y value is 1, we can start to solve for x. Now this one's not as convenient as square rooting the 2 produces an irrational number. Kind of makes sense because it's in between a 1 and a 2, so it's not always a perfect value. So the square root of 2 has a y value of 1, and the square root of negative 2 has a y value of 1, and these are the other pair of invariant points. And lastly, a bit of a conceptual question. We've been talking a lot about full and complete functions, and what would happen if we talked specifically about individual points. For example, 3, 4. You can imagine that there is some broader function happening, and I won't sketch anything, but there is a point 3, 4. Where would this dot change to? Where would this transform if we took the square root of the y value? I led that a little bit. We're only square rooting the y value. So this would travel straight down, x doesn't change, to a 3, 2. Many people would look at an example like letter B and see negative 2 and a 5 and say, oh, there's a negative, this doesn't work. But if you visualize where negative 2, positive 5 is, it can travel straight down to a new y value, negative 2, root 5. This last one was intentionally given as a bit of a challenge because if you again visualize this one, 7 right, 3 down, negative y value, this one does not exist. So last day we were talking about transformations. Today we're talking about square rooting a function.